Okay, good morning. Sorry for keeping you waiting. So I would like to start our tutorial session. So first, I would like to thank everyone on site and online for our tutorial on optics for beta AI, capturing and synthesizing realistic data for low light enhancement. First of all, I would like to introduce organizers and the speakers for our tutorial. Today we have Mr. Yunhao Zhou. Yunhao, can you say hello to our audience?
Hello, everyone. I am Yunhao Zhou, and I am a third-year PhD student at Beijing Institute of Technology.
Okay, yeah, thank you very much. And we have Haiyang Zhang. I think Haiyang is on site. Haiyang is now a PhD student in the University of Tokyo, and Yin Fu, a professor in Beijing Institute of Technology. Hi, Yin, can you say hello to our guests? Yin, can you hear me? Okay, I will skip this. And finally, me, Yin Qiangzhen from the University of Tokyo. First of all, I have to say sorry because of visa issues. We have to, three of us have to run this tutorial session remotely. And here is the schedule today. After a brief opening remarks, Yin will give us a talk on low light image enhancement. After that, Haiyang will give us a talk on low light video enhancement. After a 30-minute coffee break, in the second half, we will talk more on the practice side. Yunhao will introduce how to calibrate and simulate noise, and me will introduce how to construct a coaxial imaging system. And finally, we will have an intense Q&A session. So our tutorial is on low light imaging. For example, imaging at light. At light time, there are still some lateral illuminance. We can measure the illuminance level. For example, the illuminance level for moonlight is about 1 lux. For starlight and skylight, that can be even lower. Let's first have a look at the performance of human eyes. Basically, human eyes can see at dark environment about like 1 lux. If we capture images with a digital camera, and we will usually find that digital cameras cannot take clean images, for example, under moonlight. If we use an AI algorithm on such low light images, basically they will not work properly as we expect. One important reason is that existing data sets for training AI algorithm do not contain enough low light samples. One strategy is to use data augmentation. However, simple data augmentation cannot deal with very strong and very complex noise in low light environment. So a natural question is how to get a sharp image at light time. There are many different solutions. For example, as for active measures, we can use auxiliary illumination in the visible range, like a flash lamp on a cell phone or headlights on a car. To reduce light pollution, surveillance camera system usually use near infrared. Oh, sorry. Use near infrared illumination. However, the color and texture tend to disappear. As for passive methods, we can use better optics, for example, a larger lens or high-end image sensors. However, these solutions are very expensive. So here comes the low-cost solution, low light enhancement using deep learning. We have seen many unsupervised methods and self-supervised method. However, because the problem itself is very complex, so we are in favor of supervised deep learning, and for which large amount of training data is very important. So how to get paired dark and bright training data? One straightforward idea is to use short and long exposure. So this method, for example, is used in this famous CVPR paper, learning to stay in the dark. However, the number of image pairs is around several hundreds, and it's very hard to increase this number. So we have two solutions, that will be introduced in this tutorial. The first one is to study optical and electronic properties, for more realistic data simulation. And the second solution is to construct an optical system for more efficient and realistic data capture. So we summarize these two solutions into a framework, and it is called Optics for Better AI. So basically, we try to create a large amount of high quality data, and with the hope that the AI algorithm can work better. So actually, this framework can be applied to many other restoration tasks. For example, deep learning and zoning shadow correction and frame interpretation. Today, our focus is on raw image enhancement. There are many different reasons, and the key reason is that the ISP module, that transforms the raw image into an sRGB image is very complex, and weak signals tend to be destroyed. So that's why we focus mainly on raw images. Also, we focus on image enhancement. For sure, this pipeline can be adapted for low light image understanding without enhancement. Okay, so next, I would like to invite Yin. So she will give us a talk on low light raw image enhancement, mostly with data, simulated data. Yin.
Okay, thank you. I will share my slides. Can you see me slides?
Yeah, no problem.
Okay. Good morning, everyone. Thanks for the introduction of Professor Zheng. It's truly a privilege to have the opportunity to introduce the topic of low light image synthesis and enhancement. This talk I will introduce from these 5 parts. First, I will briefly introduce the background of low light enhancement, as well as a review of recent advancements and trends within this field. Then I will talk about low light data capture, synthesized based on noise modeling, performance of enhancement result. Lastly, I will introduce attempt on low light video enhancement. First, let me introduce the task of low light enhancement. Low light imaging is a very challenging task due to limited photon count. Wide lighting condition results in loss of image details, color distortion, low signal to noise ratio, and so on. As a result, the visual perception quality is severely damaged, and such low quality images usually fails in various downstream vision applications, including object detection, depth estimation, and so on. To deal with the image limitations, a specific task known as low light enhancement has emerged. This fundamental goal of this field is to improve the visibility and quality of imaging taken under fully illumination conditions. They not only enhance the aesthetic appearance, but now also significantly improve the performance of subsequent vision applications. Previously, the transformation of low light images into normal light ones has been largely employed in the standard sRGB domain. This domain is close to the color perception of human eyes and is widely used for storage and propagation. Built on the traditional Retina-X theory, the Retina-X offers a significant contribution to the field of sRGB low light enhancement. The Retina-X theory is a color vision theory which assumes that the color of object is determined by its reflectance and separates from the illumination conditions. Retina-X adopts this fundamental principle and takes it a step further by incorporating deep learning methodologies. ZDCE method is the first low light enhancement network to operate independently of both paired and unpaired training data. It allows it to operate more flexible and adaptively in real-world application, where paired data are often unavailable. Enlightenment has revolutionized the low light enhancement by proposing a novel approach that integrates GAN with a self-regulation attention-guarded unit architecture. Although sRGB low light enhancement has achieved promising performance, it has some inherent limitations. One of the key issues with sRGB is its limited bit step, confined to only 8 bits. This restriction significantly hinders our ability to enhance imaging taken under extremely low light conditions, like the moon or under starlight. Another problem is that sRGB images are passed through camera image signal processing pipeline. This pipeline transforms the image into a nonlinear space, which makes it exceedingly difficult to model noise. Noise is in this nonlinear space is complex and heterogeneous, making it challenging to effective modeling and remove it without compromising the imaging overall quality. And instead of RGB image, linear raw images have higher bit steps. Usually it can be 10 to 14 bits. Thus are naturally more suitable for low light enhancement, especially in extremely dark conditions. In the next, we will dive deeper into how raw images are processed and enhanced for better visibility under extreme low light conditions. Due to very limited photon count and inescapable noise, extreme low light imaging is much more challenging. This picture on the left is a low light image taken by a camera with a short exposure in a nearly lightless environment. Under such extremely low light conditions, even humans can't observe and perceive any information from it. Although we can increase the brightness of the image through post-processing method, like the right one, such as a digital gain, to get the normal brightness image on the right. However, in this process, the noise signal is also amplified at the same time, so that details of the image seen are almost completely lost. Different from sRGB low light enhancement, the primary task for low light raw enhancement is to reduce image noise. To obtain image with higher signal-to-noise ratio, there are some hardware-based solutions, particularly some advanced sensors. These sensors, characterized by their strong sensing ability and high signal-to-noise ratio, are specifically designed to recall in challenging lighting conditions. Although low-light imaging can be achieved by hardware-based approaches using advanced low-light sensors, our interest here lies in computation-based denoising, which could be applied to cameras without the need for dedicated imaging hardware. Along this line of research, significant progress have been made in past few years. Among them, traditional methods often rely on handcraft approaches such as smoothness, fastness, low rank. These pairs are based on certain assumptions on image characteristics, and they guide the design of the denoisers. Recent work is a burst a processing scheme which aligns and views a burst of photos to increase the signal-to-noise ratio. Nevertheless, such burst processing method may generate unwanted ghosting effect when capturing dynamic scene in the presence of vehicles, humans, and so on. More particular and powerful methods are built on deep learning tools that automatically learn the mapping between a low light noisy image and its long exposure clean images. The deep learning approach usually requires a large value of densely labeled real training data, which is tremendously difficult to acquire. Obtaining quality training data is crucial for supervised deep learning method. So a fundamental question arises: how to obtain training data? Generally, there are two approaches to gather training data: using raw images or generating synthesized ones. Each approach can come with its own advantages and drawbacks. Real image provides ultra real-world representations, but can be time-consuming to collect and is limited to static scenes. Synthetic data is easier to generate in large quantities. but its effectiveness depends on the accuracy of the generation models. Now let's come to capture the real-paired low light training data. In order to enhance low light image by deep learning method, we need to capture paired low light and normal light images. The input low light image is acquired using a short exposure time, which captures less light and results in a noisy image. To obtain the clean target of the well-exposed image, two methods can be exploited. The first is utilizing a longer exposure time, which allows more light information to be gathered, thereby reducing noise. The second method involved force capture, which involves taking multiple quick successive images of the same scene. These images are then averaged or merged to reduce noise and enhance the signal, yielding a cleaner, well-light illumination image. Tactical data capture procedures and setup are shown in this slide. The camera is mounted in a sturdy tripod and controlled by a remote software to avoid misalignments. For each scene of a given camera, a reference image at the base ISO was firstly taken, followed by noisy image, whose exposure time was deliberately decreased by low light factors to simulate extreme low light conditions. Following this procedure, the SID dataset uses two cameras, 3 low light factors for each scene, and totally captures 5,094 raw short exposure images with the corresponding low long exposure reference. This dataset contains data for both training and evaluation. The RV dataset captured 200 tools that take low light videos using the same way as the image captures. ELD dataset chooses 3 ISO and 2 low light factors for noise imaging to capture dataset, resulting in 240 raw imaging pairs in total. This dataset is just for testing, not for the training. Real data capture, while valuable, comes with its own limitations. First, the process is laborious and time-consuming, restricting the volume of collected data. Secondly, this limited scene variation can narrow the range of the situations that the trained model can handle. Third, the dataset size is inherently limited due to the constraints of capture. Last but not the least, only static scene can be captured to avoid issues like motion blur and misalignment, which are common in to obtain training data, which is
Sorry, Professor Fu, sorry about the interruption. There is just a little glitch about the connection. We lost you for about 15 seconds. Can you just wind back a little bit?
Can you see this
Thank you.
26 page? Okay, I will start it from 26 page. To overcome the limitations of real data capture, we will introduce another line to obtain training data, which low light data synthesized based on noise models. As we have mentioned, noise is a key degradation process for low light image in raw domain. In other words, once we model the real sensor noisy distribution accurately, we can synthesize realistic noise from the noise model and then add edge to the clean image to form a synthetic noisy image. With the original clean image and the synthetic noisy image, we get a pair of training data. In this way, we can obtain large and inexpensive training data set for low light image enhancement. The procedures to enhance low light images using synthetic data. First, noise distributions are modeled by the statistical or deep noise models, such as Gaussian, Poisson-Gaussian, physics-based noise model, and so on. Then we generate noise for existing clean images to have a large paired training dataset. Finally, the synthetic dataset is used for training deep neural networks. A crucial point here is that noise modeling strives to accurately emulate the distribution of real sensor noise. The successful noise models reduce the simulation to a relative gap, which in turn boosts the performance of low light image enhancement on real-world image. Hence, effective noise modeling is an important component of generating reliable synthetic training data. Some early works are built on Gaussian noise model. For example, this method uses CNN to predict the pixel-wise Gaussian noise level. To synthesize more accurate noise, this method utilizes Poisson-Gaussian noise model. This model takes into account the real sensor imaging process and considers two types of noise. For example, the signal-dependent short noise and signal-independent read noise. Short noise follows a Poisson distribution and is a result of the inherent variability in the number of photons sensed by the detector. Read noise, it follows a Gaussian distribution. It's caused by the electronic circuitry associated with the sensor. For convenience, the Poisson Gaussian is approximated by heteroscedastic Gaussian. Poisson Gaussian noise model is also used in unprocessed imaging from lens raw noise denoising, which improves the model's applicability in sRGB denoising. Deep generative models have been increasingly utilized to model real-world noise accurately. A notable example of this is noise flow, which crafts a conditional normalizing flow with the imaging processing pipeline. It conditions on elements such as intensity, camera tab, and ISO settings. We also see the application of GAN in deep noise model. In this approach, a discriminator is used to discern between real and synthetically noise images, thereby learning the noise model. The framework also incorporates a camera characteristics encoding network, allows the model to learn the emulate specific camera-induced noise patterns. This generative noise model requires paired training data, which is not always accessible. Here, noise-to-noise flow further enhances the application of noise flow to quickly supervise the condition. Rather than using noise and clean image pairs for training, this method can model noise distribution with pairs of noisy data. When it comes to extremely low light conditions, the above noise models may fail. The challenge arises from the fact that the real noise distributions in these conditions are significantly more complex than those described by Gaussian and Poisson-Gaussian models. Moreover, the actual noise components tend to be intermingled and are challenging for deep generative models to learn. New modeling strategies are necessary for this challenging condition. Now, I will introduce more accuracy noise models, which are built on the physics information process of images. We call this method as physics-based noise model. The first work to employ complex physics-based noise model is this one. We called it ERD. It finally models the various noise sources involved in the physical process of electronic imaging, from photons to electrons, then voltages, and finally to digital signals. It includes the photon shot noise, readout noise, draw noise, and quantization noise. Photon shot noise is derived from the quantum nature of light and can be modeled by Poisson distribution. Readout noise is the sum of various noises introduced during the readout process of a photoelectronic signal through the sensor circuit. By mimicking the distribution of noise component that emerge at each step of the image formation process, ELD provides a more realistic representation of actual noise. In contrast to ELD, which models each read noise component separately, another approach involves directly sampling with noise from actual dark frames. In this method, signal-independent noise is sampled from real noise frames, offering a more aesthetic representation of the noise. Additionally, a high-bit reconstruction strategy is employed to synthesize synthetic raw noise. Furthermore, this method propose the dark shading model and correction as a vital preliminary step. In this work, dark shading is calibrated first in terms of different ISO settings and then corrected by being subtracted from noisy images. To more precise noise representation, the GAN-tuned physics-based noise model has been developed. It model integrates the power of GAN to tune the physics-based noise model, thereby representing camera noise more accurately. Such fine-grained noise models proves to be particularly beneficial in the most challenging lighting conditions, such as starlight conditions. The improved accuracy in noise modeling under these extreme low light conditions enhance the potential for better image qualities. A recent work proposed a comprehensive approach that leverages normalizing flow under a more complete static noise assumptions. stage work at this one. First, okay, can you hear me?
Yes, Professor Fu, can you go back to page
Okay.
40? And thank you.
Go to 40. Okay.
Yes.
This work modeling the method considering the ISO dependence. With this is established the noise models. The data synthesized procedure works as follows. First, we start with the clean imaging, second this one by applying an exposure ratio, simulating a low light condition to procedure what we refer to as a low light clean image. Next, we generate noise using the noise model and add this to the low light clean images. This gives us the synthetic noise image under the low light condition. Generally, this synthetic image are then brightened before feeding them into the deep learning model for further processing. In this way, we have paired training data for low light enhancement. Now we have learned how to model real noise distribution. Let's shift our focus to the performance. Here, let's take a look at the performance of some of leading methods in low light enhancement. This method trained the low light enhancement model on paired training data and proved to have very inspiring enhancement performance compared to the JPEG images produced by the camera. It shows that it can be works much better on the RAW format than that on the JPEG sRGB domain. This result shows that the accuracy modeling noise model trained on synthetic data can get comparable results to one trained with the real data. This result from the real data training is from the synthetic data, producing visibly appealing outcomes. Besides, applying physics-based noise and model has been effectively for denoising shadowed regions on the moon. This is the moon results, and this is the denoising results. Furthermore, under starlight conditions, with only 0.6 to 0.7 millilux and no active illumination, synthesized data had proven valuable for enhancing image quality. These cases illustrate the considerable potential of computational method in low light image enhancement. We have demonstrated the performance of the on improving visible qualities with the real or synthetic training data. Here we further show the low light enhancement. It could be helpful for other downstream computer vision applications. Here we can see in this picture, the enhancement operation significantly improves the low light objects recognition accuracy, especially the teddy bear is accurately recognized by Google Vision API. Such improvements are consistent on object detection in the dark, in monocular depth estimation, and in the optical flow estimation in the dark. This demonstrates the effective of raw low light enhancement in a wide range of low light vision applications. Okay, finally, I will introduce to attempt to low light video enhancement. By directly applying the physics-based noise model on low light video synthesis, we can see that the enhanced result still arrived at the performance comparable to the paired real data However, the writer using Kepler synthesized low light image data would struggle with flickering effects. As a result, a real low light video dataset and the method are required for temporal consistency. Okay, that's all I wanted to share with you today. Thanks for your attention. And next, let's welcome Haiyang to dive into the explorations with the training data and the method for real low light video enhancement. Thank you.
Thank you, Professor. Hey. Good morning, everyone. Thank you for joining us in on-site and online. And my name is Haiyang Zhang, and let us begin the journey into the low light video enhancement. So continuing what Professor Fu just introduced about attempts on low light video enhancement, we kind of raise a natural question, and is there a better option than temporal consistency priors? The answer is yes. Let me introduce you to the advancements in datasets for low light video enhancement through the details of techniques and what conclusions we can, insightful conclusions we can draw. So the main contents of this section will be divided into background introduction, the detailed techniques for dataset capturing, and the attempt experiments we carried out on the captured data versus synthesized data, and also the conclusions. So let's begin. In the low light video enhancement, there is a strong motivation in the real-time applications, such as mobile videography, surveillance cameras, video conferencing in the backlighting situations, underwater exploration, macroscopy, and autonomous driving in the night, etc. So basically, traditional methods on the low light video enhancement can be divided into 4 categories. They either depend on the redness theory, dividing the image into illuminance and reflectance, or they use gamma correction to nonlinearly change the pixel values. They also can borrow the image dehazing techniques to simulate the particle interactions. And finally, there is a grouping of similar patches across the temporal and spatial dimensions. The last patches grouping method to today still remains one of the state-of-the-art traditional methods. For example, VBMD 4D is always considered one of the baseline to compare with the data-driven methods. So stepping into the data-driven era, there are some early attempts into simply modify the network structures, including recurrent network or residual network, or just using multi-branch encoder-decoder structures to enhance the overall visual effects. And there are also 3D convolutions that incorporates temporal information through a sliding window fashion that it kind of continuously process each part of the videos. There's also an upgrade to the 3D deformable convolutions in this line of work. And finally, to explore more into the self-similarities shared across the video sequences, there are attempts to try to extract the aligned information from adjacent frames, whether through explicit optical flow warping, like the work shown here, or through the implicit UNet transformations. There are also incorporation for the attention mechanisms on the temporal self-similarities, and all this work introduced here in the data-driven era, they show us the potential for the low-light video enhancement. But what actually determines the upper bound for low-light video enhancement effects is actually how much data, how much information is still remain in the data set, which brings us to the next part, that how can we effectively or perfectly capture the paired data that we want, a degraded dark input and the clean, bright ground truth for the video enhancement training. So as mentioned by Professor Fu before, there is actually an extension from the image methods, which is to use long exposure. And naturally, as the previous work, learning to see in the dark, it's actually used the long exposure together, paired low light images and ground truth bright raw images. So they have a follow-up work, which is to use the capture the long exposure to capture the ground truth for static videos. For those videos, there's no motion, no camera motion, no object movements, and all the frames in one video sequence remains completely the same with only time varying noises. So the ground truth is noise-free, can serve as the ground truth. The one image can serve for the ground truth for all the frames in one video sequence. And those static videos free from the motion and background motion or camera motion are statically used to train the network and then extended to the dynamic scenes. It is carried out through a residual UNet and with multiple loss functions carried out on each frame between each other, between adjacent frames, the consistency loss, and between the predicted result with the ground truth. So this data set has has 202 raw videos, and the ratio is between 120 and 300. The ratio here is defined as the ratio between short exposure time and long exposure time. As the photon energy accumulates through time linearly, that ratio should be reflected linearly in raw sensor data as well. Namely, if we have the ground truth and the raw dark input, their mean values of the raw sensor data should be roughly this ratio, given that the existence of the noises might perturbate the ratio a little bit. So with the upcoming introduced data set, this ratio concept is kind of remain the core in the low light or extreme dark video enhancements. So in this sense, we have static videos, but what if we want to incorporate more motion or movements into our data set? There are, as mentioned before, this long exposure method doesn't have movements from the camera, nor the movements from the objects. So from these two aspects, we can try to control those motions, introducing the controlled motion data sets. So first, the SDSD control camera motion through an electric sliding guide rail, and CRVD through the controlled object movements. As can be seen here, the SDSC dataset has an electric guide rail with 1 millimeter position margin of error. So it can reproduce its programmed motion multiple times. If we mount the camera on the platform and then capture multiple sequences, with one of them being bright, the other one being darkened by a ND filter, then we can have the paired data of the raw input. So the ND filter stands for neutral density filter. It dampens light without color shift. Namely, it reduces the magnitude of electromagnetic waves without in all the spectrum equally. So the ND filter guarantees us we can have the dark input, and the another run without the ND filter can give us the aligned bright ground truth videos that we want. Another detail here is that, as you can notice on the right side of the illustration, there are different colors along the guide rail. That is because the program motion is actually divided into several phases, including acceleration, constant speed moving, and then decelerating. So the most ideal part is to align the videos through the constant moving phase, which is the orange color here in the center part. So actually, the alignment here requires some human labor to manually decide which frames to keep, which frames to get rid of, and that's one part of the laborious essence of this method. But still, it can control camera motion in a limited way through the 1D sliding and get the moving scene with proper camera motion and align the data that we want. So as mentioned, another controlled motion, this is just samples from the SDS data. And another controlled method for this motion data set is to control object movement. Namely, imagine a stop motion animation. It moves objects through the frame one by one, and then even though human perceptions gather those information through a time axis, we perceive those videos through time along the time axis. But when we move those objects at a certain given position, we can take multiple frames at the same time. So all those frames gathered with the scene contents that we want, namely the foreground moving object and the time varying noises. With the multiple take of the single frame at multiple times, we can average them to extract a noise-free ground truth frame and group all and repeat that process for all the frames. We will have multiple noisy videos and an average noise-free ground truth. In this sense, they can actually create the perfectly aligned noisy input and the noise-free ground truth. And here are the examples for the collected data. The first two rows are in raw format, in raw domain, with noisy on the upper row and clean on the second. And the last two rows are in RGB format. And you can see the motion of the toy in the foreground here is carried out frame by frame. And this capture actually leaves the motion blur that actually naturally occurs in our video capture. It leaves that out of the picture. So even though it can give us a paired data, we still want more information to be encoded in the spatial and temporal information in our data set. So introducing another way to gather data, which is through the beam splitter method. This is the core optical system used in seeing moving object in the dark SMOID dataset. You can see that here the key factor is the beam splitter. The incident light is actually adjusted by the relay lens for the proper depth of field. And the incident light is then divided equally by the beam splitter fed to the two separate cameras. And each of them can be synchronized by a signal generator. And one of the camera 2 here is equipped with an ND filter as introduced before to dampen the light, to attenuate the light intensity, so that camera 2 will give us the dark degraded input, and the camera 1 will have the bright ground truth. In this sense, both cameras are actually looking at the same light signals, and they can be aligned perfectly, both spatially and temporally in this sense, gathering both the scene content and the motion blur information that we want. But for this optical system to work, there is still another important factor to key in, which is the alignment between the captured images, frame sequences from those cameras. Actually, here there is a pre-step before each capturing. We have to remove the ND filter first, so that both cameras can take the bright pictures and use those two bright pictures, extracting a homography transformation through feature matching. Subsequently captured sequences can be warped to enforce a pixel level alignment, so that we can align all the data that we want. And here are the example datasets, example frames from the dataset. And to be more specific about this dataset and its project, it is trained simply on a 3D unit with its convolution layers changed to carry out in 3D both spatially and temporally. And the original paper with this simple upgrade can achieve the state-of-the-art performance at the time. And later with multi-scale training and multi-loss enforcement, it can actually have better results, as can be shown here to see how it performs in the real-world night video. The captured almost dark video can be enhanced to vivid colors, and with the updates on the networks and the algorithm, you can see actually the characters, the shapes, the colors can be more perfectly restored than before. And this is the power of AI applied to low light video enhancement. Okay, so we've already introduced several methods, and there's a new method come very recently, is to capture dataset from a monitor. And as can be shown here, as can be shown here on the upper left, there is a picture of taking the bright video frames from a monitor. And actually the algorithm here, it has to guarantee that the distance of the camera and the monitor should eliminate the Moore pattern that is demonstrated on the usual digital monitors. And also it should ensure one monitor pixel is smaller than a camera sensor pixel to have a authentic video frames captured by the digital camera. And as mentioned before, the ratio here is drawn from the 100 and 320, so that in this sense, the different frames of different videos is actually captured frame by frame, and each of them will have a reference exposure time set to perfectly capture the video frames at the ground truth level, and then that exposure time is divided by the ratio, by the randomly sampled ratio for the single video, and then take the noisy frame. In that, once the camera is sturdily mounted on a tripod, all this process can guarantee a perfectly aligned structure for the input gathering and the ground truth gathering. And here, for this data set, the authors also discussed how diverse the motion exists in different data sets. As introduced before, SMID, see motion in the dark, completely static videos. There is no motion in there. And CRVD, the stop motion fashion of gathering video dataset, has very limited only in 3 directions. And SDSD, the guide rail method, has only 0 and 180 degrees align those axes, the movements. So it's very limited to 1 dimension. And in the monitor capture data set, you can see the diversified motion can be captured in this data set, which actually facilitates the performance gain for the network and algorithms a lot. And it also verifies how realistic are the noise captured through the monitor. As you can see here, the x-axis is the noise distribution from the real world frames, and the y-axis is actually noise from the captured on monitor frames. You can see those dots actually align perfectly with more than 90% R square, and through multiple ISO levels, the noise actually is authentically recorded in the monitor captured process. So basically, these are all current popular or the feasible way to gather low light video dataset. And to simply recap those datasets, we can see in the motion part, just mentioned before, the SMID, no motion, CRVD, the foreground object stop motion, and SDSD only have 1D, limited 1D camera motion, while SMOID, the beam splitter one, and monitor capture one has more diversified motion. And the number of video pairs in each data set is around from 50 to 200. And this number is not great compared to specifically image data sets, but considering each video pairs contains multiple frames, so the capacity of all these data sets are quite huge. And most of them contains multiple noise levels to further span more diversified situations, simulating the real world capture sequences. And for the domain, as you can see here, most of the data set actually targeted the extreme dark video enhancement. So most of them are in raw domain, with only one of them is in RGB. And the ratios here, the SMID and the monitor captured data set are actually from 100, roughly from 100 to 300, targeting the extreme dark cases, while CRVD, the stop motion captured data set, is actually, the ratio, if we calculate, it should be 1 because it only takes average of each frames directly. And the SDSD doesn't report its ratio, and the SMOID dataset has 100 ratio for the ND filter and the 5 different noise gain level to more diversify the noise level. And for the equipment needed for each dataset capture, there is actually only tripod needed for the first two, the SMID and CRVD, and maybe a remotely controlled camera. You can sturdily mount the camera on a tripod and capture the perfectly aligned dark input and bright ground truth. The SDST requires a high precision slide rail, and the SMOID dataset requires a coaxial optical system, which will be introduced more in detail in the later sections of this tutorial. And the monitor dataset only requires a monitor and digital camera. So basically, these are the overview of the current existing dataset for low-light video enhancement training. As you can see here, there are a lot of dataset that requires laborious process to build the optical system or to capture the different motions of foreground objects. And all of this labor, if those can be saved to synthesize the data, it would save a lot of efforts to actually gather high quality low light video enhancement data set. So we want to test the assumption, because here, as the Professor Fu introduced, we only have multiple image noise synthesis. The noise modeling for digital image has been analyzed a lot, but there's seldom or few to none instance actually devoted to noise modeling in dark videos. So we want to test whether those synthesized frame by frame of the image noise modeling can be directly added to the video, and can they compete with the captured real-world low-light video datasets. That's the main idea of the upcoming part. So, as introduced by Professor Fu, there are a lot of synthetic models for different noise modeling. And for the simplicity, we only take the ELD here to use a physics-based noise formation to add noise frame by frame to our videos. And together, the real-world videos, we use the formerly mentioned coaxial optical system to capture multiple ratios of different aligned video pairs. And as you can see here, we have three ratios: ratio 10, ratio 30, and ratio 100. Again, those ratios reminds the roughly coefficients between the raw ground truth and the raw input. So the raw ground truth is roughly 10 times, 30 times, or 100 times brighter than the raw inputs. And we also incorporate the camera analog gain compensation to further approximate the real world situations. Because in real life, we usually in the dark situations, we use high gain level, namely the high ISO settings. And if we want to gather the ground truth, we are using low ISO and low exposure. So in this sense, the analog gain is actually more, it's closer to the ISO we have in the consumer grade cameras. So specifically here, the ratio 10 and ratio 30 has camera analog gain completely compensate for the differences between the raw input, namely the raw dark input is not that dark as can be seen here in the second row. It actually contains the noises, perceptible noises, but the brightness is actually already compensated by the camera of 33 in terms of linear ratios. So there's still roughly 3 times of the brightness differences between the ratio 100, which is on the rightmost column here. As you can see here, the actually brightness is not completely matched. So in this sense, we want to approximate the real world. For example, the photographers might not choose the perfect ISO, and whether we want to test whether the model can deal with those situations perfectly. And as mentioned before, we use ELD noise model to calibrate all the necessary coefficients for the noise synthesis. So namely here, the noise N is divided into 4 parts. The K is the overall system gain. calibrated by flight view frames. And MP is the Poisson distribution sharp noise. And read stands for read noise, which follows a Taki-lambda distribution for each pixel. And NR stands for roll noises, which for each roll, there is a Gaussian normally distributed perturbations. And finally, the NQ stands for quantization, a uniformly distributed noise factor. So finally, for our experiment, we train a video, or one of the latest video restoration models, the basic VSR++, and modified its original inputs from the RGB domain to raw domain. And basically, these are our settings to compete against how this model trained on the real capture data through the coaxial systems and the synthesized system calibrated with the noise parameters from the same camera. We want to test how those two compete with each other. And here are the basic results. So simply here, in the middle column is the synthetically synthesized data trained model. You can see it performs better than the real world data without digital gain. And it's performs slightly worse than the real world data trained with digital gain. As mentioned before, in ratio 100, there is still a gap between the ratios. So the digital gain here is to fill that gap with directly multiply a ratio onto that input. So as you can see here, the digital gain actually helps the real world a lot, and synthesized data can actually beat the real world data without digital gain. So this actually says that using the synthesized data directly in a frame by frame fashion into the video enhancement, it can actually achieve like the performance that is better than the naive solution to directly feed real world data into the network. And as can be seen from the title of this picture here, this is the test result from the original three ratios, ratio 10, ratio 30, and ratio 100. We further gathered several other unseen ratios that are not used in the training process, ratio 20, and we test that all those models on the ratio 20 test set. As can be seen here, the synthetic data set actually has better PSNR than the real world with digital gain, and also better SSIM than the real world without digital gain. As can be seen here, the synthetic data set with randomly sampled ratios from the original ratios 10 to 100, it actually covers ratio 20 test set much better than two other methods here. So in this sense, we are using, at the time of the experiment, we haven't used the very latest synthetic models, noise models, but still with the original ELD model tests synthetic way, we can already achieve in the low light video enhancement the results that's comparable and sometimes better than the real world captured data. So this is proof of feasibility, proof of concept that the synthetic noise data set, how can they work in the real and synthetic low light video enhancement. So basically that covers up most contents that I would like to share with you today. And for the completely overview about the low light video enhancement and the low light, especially the data set that used for low light video enhancement, there are actually two ways to understand what I've just introduced to you. The various ways, novel ways of capturing data set through the physics testing or the optical systems. They are the exterior exploration on how to get the low light video data set that can capture more and more information, more motion, more dynamic scenes, and more blur information into the data set, raising the upper bound for the network and algorithm solutions. While on the other hand, synthetic data set is an interior investigation into the physical details inside the digital image formation. So these two actually should combine together to evolving with the low light video algorithms and networks to help better facilitate the advancement of the performance on these tasks. And basically, in essence, what we're trying to do here is trying to deal with information loss in the integrated input, and whether in the dark or noisy inputs. So to the extreme, there's still a lot to explore in this area about the tasks, whether without the HDR, the saturated pixels, how to restore those information from adjacent frames, the self-similarity shared across frames, or in the extreme dark places, the precision limited situations where the information is lost in digital through the analog to digital converters. And all this are still remaining a open question that can be answered with the advancements of both exterior and interior investigations on the low light video enhancement and data sets. And that is all I want to share with you. Thank you so much. Have a good coffee break.
Okay, Hayang, thank you very much.
And then you have data classifier section. How good is this information using this model? Yeah, it's a sort of a hybrid between purely synthetic and the real data. What that is helpful.
Demonstrating videos on the model is the real world video stream contain all that information. Actually, I haven't directly but through the paper published by the authors, they test the also distribution, the depth, whether it affects the end results or not. And the answer is no, it doesn't matter much because the noise number relates to signals. That's information can be able to do sense. So just to build from the response, or the essentially good enough.
Because you have the real from the family. Exactly. It's a real capture, but the actual content doesn't matter much. Exactly. Like this is like this one something so they may move a little bit. So in that sense, it's a better way to do it now. In the large scale collection using this way.
This is my lesson. Since I take on and last year,
do you find it? You know, some always do it quick, so this is a great time to set up.
I haven't tried it yet. It's really sort of system. You're still in knowledge, it's reasonable to that.
I want to check more later of this session. Do you have a weekend of looking at later of this session? Yeah, I was a message in last night. I was hoping to see him at the conference, but not here. It's a when you got a food, you got that. I'll check you later.
Or video things. Similar. So that's why it has to be. Otherwise, so you can see those. Oh, simple, just time into by multiply by because you know the total energy cost of the sun linear and the low sensor signal is also proportional to the energy. So in this sense, the time is similar to apply that amount of energy. That's why we use yeah, evolution bias. Yeah, that's actually due to the actually calling like bias or something like that. As relates to the manufacturer of each sensor has different effects on the sensor business. So it might be more sensitive to that for you. So that it was bias. Those bias were not the main reason that the extreme amount of this is very
I just wanted to check that all the technologies were.
it's so fast. Okay. So it's not a law. That's me.
Is there any technical
For the specific project, I mean, the final experience. Yeah, actually, we're not so currently this is but still someone in the test. So we are still working as well. We're actually doing the current state of the business. So maybe we're this year, it's definitely one of the reports to commission this one as a paper.
And if your paper they show that synthetic data set could has performance as more as
Yes.
why you show that it's not.
Oh, yes, because once information is those papers actually working image like this is video. So there's a difference in temporal information. Currently association with the what consideration that so they're actually if we have to central formation the circuit also other all some of them some truly that cross correlation. They have like not a random distribution, but like a random system.
I read to see your those things, so not like structure those system. Yes, so I have a higher. I read to see what your I have been following the I put some photos. So let your paper. And how long did you take to collect data?
Oh, yeah. That varies for different reasons, but just for the whole of the system, you might take some time to build it because you have to ensure everything is connected steadily, and also there are other things that we can enforce or aligning different things. That will take some time for you or also that. But other than the data is in my opinion, it's very common because you don't have to stop. You just take normal videos and all those information. So that's the most important. All other data is either stop or they have to do this. That's consuming.
I also propose blood else use the kind of system. So so I really drive you.
I don't know.
Doesn't it?
Just one second.
Service, maybe part of it is here, where it's quite low. You can see it here, and here I can check this. So there's and there's lots of there's low maybe the exposure is too low and the other problem is that since I'm not doing the light reflection is less powerful than actually the lens for the lens is really lost the lights and since I'm not using the lens I use the but it's really bright, right? screen pretty bright, but I don't want to make it too bright to the rest of the section. This is weird. I mean, it's weird if any time it is bright window, right? Or yeah, no, I didn't know anything else. But in that case, I mean, how about that same thing with that? There's also because yeah, yes, I'm only working this picture, but to get to this picture. So there are most of the private. So at the moment I'm only doing, so I take this picture and what I have with this reconstruction I'm going to use this here that I have a PSF with my camera and I kind of do a decompose on to get this just deconvolution and so I could still put the denoise that they have exposed, which is something we tried and then got another result.
And the spruce reaction.
Yeah. But yeah, this is pretty much only deconvolution. So maybe in the denoise there would have to there's also a very unique type of noise that we have in the streets. It's quite nonsense. But I found all hard selection. So my current pipeline that I didn't have everything. But the unit is just that someone else. Yes, the sensor reuse is cheap. And also, it has to be started by the when you make this only so even for this mask, then yeah. And then the other aspect is the algorithms to really with no fingers say and the other is the other aspect where inside is package
Okay, so it's almost the time. So we would like to step to the second half. And first, Yunhao will give us a talk on how to calibrate noise and how to simulate dark and bright images. Yunhao, I will. Okay.
Okay.
Would you please share your screen?
Okay. Can you see my screen?
Yeah. Yeah, no problem.
Okay. So let's get started. Hi, everyone. Welcome to the second half of our tutorial, Optics for Better AI. My name is Yunhao Zhou, and I'm excited to delve deeper into the topic of camera noise modeling and calibration with you. As a follow-up to Professor Fu's talk on low-light imaging synthesis and enhancement, this section aims to explore in greater detail the concepts of noise modeling based on real image formation pipeline. We will also look into essential calibration data and understand the process of calibration noise parameters for specific cameras. This talk will not only cover the theoretical aspects, but also provide practical insights, including a walkthrough of noise modeling calibration and noise image synthesis in practical situations. Okay, first, I'll talk about the noise modeling based on image formation pipeline. To understand the image capturing process, let's take a look at the physics of image formation. The process comprises of several stages. To begin with, the CMOS sensor receives the signals in the form of photons, and these photons are then transformed into electrons, whose accumulation further generates the voltage. And lastly, the EDC transforms this voltage into a digital signal and result in what we know as a raw image. However, each of these stages introduce certain noise components. For instance, the conversion from photons to electrons is subject to uncertainty in the number of particles collected, leading to the Poisson-distributed short noise. And similarly, the process of converting electrons to voltage can introduce several types of noise, including raw noise, thermal noise, direct current noise, and fixed pattern noise, and so on. And due to the electronic components and the readout formats. And lastly, the conversion from an analog to digital signal brings about the quantization noise, which is inevitable during the ADC process. And okay, understanding the physical pipeline of image formation, an influential work known as ELD categorizes the primary noise sources into 4 components. That is the photon shot noise, readout noise, stripe noise, and particularly the raw noise, and also the quantization noise. And photon shot noise arises from the inherent uncertainty of light at quantum level, and is typically modeled by a Poisson distribution. Readout noise is the sum of various noises introduced during the readout process of photoelectronic signals through the sensor circuit. While the Gaussian distribution has been commonly used to describe the readout noise, the ELD model uncovers a long tail characteristics in it and subsequently uses a tachy-lambda distribution for a more accurate representation of readout noise. Raw noise is related to the CMOS circuit readout pattern, and it is modeled through a row by row Gaussian distribution. And finally, a uniform distribution is used to model the rounding error in the ADC process, and it is called the quantization noise. As a summary, the physics-based noise model proposed by ELD includes 4 main noise components, and the different noise components models need to be specified by different parameters, including the system gain K for short noise, and the shape, color bias, and the scale parameters for the tachy-lambda distribution for read noise, and also the scale factor, the scale parameter for raw noise. In recent developments, a more comprehensive noise model has been proposed that includes additional noise components. This includes fixed pattern noise, black level error, and also the current short noise, among others. By accounting for these finer-grained noise elements, this model shows promise in further improvements in extreme low-light imaging capabilities. Okay, after understanding the recent effective noise models for low-light enhancement, let's move to how to calibrate these models. First, I will introduce the essential data we need for calibration. To calibrate these noise models, we must first recognize that the noise components we have introduced generally fall into 2 distinct categories. And the first category is the signal-dependent noise, which fluctuates with the signals. And short noise is the primary example of this kind of signal-dependent noise. And the second category comprises signal-independent noise, which remains consistent across both conditions and isn't tied to the signal. So it will not change. It will not change in different situations. The majority of noise components belongs to this kind of this type of noise, signal independent noise, including red noise, fixed pattern noise, dark current noise, and real noise. Okay, and given the distinct characteristics of each category, we must collect specific data for each type. And generally, to calibrate the signal-dependent noise, we need to capture a sequence of flat field frames. Meanwhile, for the signal-independent noise calibration, since it is not related to the illumination, we should capture the dark frame. Now let's discuss some methods for capturing the flat field frames. The aim of this frame is to offer samples with wide range of signal intensity values, and this can be achieved through varying illumination or varying the exposure times. And so one straightforward method is sensing on a uniform wall. This involves having the sensor uniformly illuminated. For instance, capturing an image of a white paper on the uniformly lit wall. And to ensure consistent results, the camera should be fixed on a tripod close to the paper with the focus set to the infinity to minimize non-uniformity. And at the bottom of this slide shows a real captured flat field. As we see, lens distortion can affect the ununiformity of the flat field frames. So to mitigate this, we can simply crop the center regions of the flat field frames. Sorry. And in addition, to account for another inevitable non-uniformity is that there might be some non-uniformity in the imaging subjects. And an alternative method is to capture two flat frames under the same condition. And subsequently, you can subtract one frame from the other in order to reduce the effect of the non-uniformity. And following this, we can then adjust the exposure time or illumination intensity and captures a sequence of flat field frames with varied intensity, which helps to cover a wide range of intensity. And in addition to the above methods, there are some simpler ways to capture flat field frames. For example, we can capture a burst series of real images featuring a static grayscale chart. The varying tones on the grayscale chart ensure a diverse range of intensity values, and the same pixel along the sequence represents the noise samples with the same latent truth signal. Another alternative is to record a standard color checker with 24 distinct patches, and each patch provides a unique intensity map sample. Okay, as for the capturing of dark frames, the capture process is different. It requires a lightless environment, like a dark room with the camera lens capped. You should use the shortest exposure time to avoid any light leakage. And furthermore, multiple dark frames should be captured for each ISO or each scan setting. And the captured dark frame would look like the left image. And by amplifying with an exposure ratio or a digital gain, we could see that the dark frames contain different noise components. And now with the calibration data captured in the next section, we will explore the approaches to calibrate noise models and estimate noise parameters. In the upcoming section, we will explore the calibration of signal-dependent noise first, which is the short noise primarily. And the short noise follows Poisson distribution by dividing the digital image with overall system gain K. We can obtain the signal in a number of photons and apply a Poisson distribution on the photons to simulate the short noise, and then we can multiply the system gain K back to the photon short noise and get the photon short noise in the in digital image space. So as for the signal-dependent short noise, the system gain K is the parameter for short noise, and exploiting the properties of the Poisson distribution, we note a linear relationship between between the signal variance and the latent true signal. And we can see that our targeted system gain K is exactly the slope of this regression. So for each flat field frame, we can compare a pair of image variation and true signal, and the paired observation can be calculated, and all of these observations provide an estimation of K, because we can model it, we can feed it with a linear regression, and the slope is just the system gain K that we want for short noise calibration. And we can notice that the intercept, we can note that the intercept term is the variance for the rest of the noise components. So when we only consider a simple Gaussian distributed without noise, the variance can be directly derived by the intercept, but we cannot derive other more complex noise models beyond Poisson Gaussian. So let's shift our focus to the signal independent noise calibration. Though the signal independent noise contains many components, as you can see, there are a lot of noise components, but one straightforward approach is to directly sampling real dark frames to represent all of them. And in this method of ICCV 2021, there is no need for calculation for any calculations related to the signal independent noise, and all we need is to store several dark frames for each ISO setting and randomly choose one when we want to sample real noise. And some alternative methods involve a step-by-step or separative calibration approach. Here, each noise component is individually calibrated, and after one component is calibrated, it is removed from the data to prevent the interference with the calibration of subsequent noise components. So we first look at the fixed pattern noise. Fixed pattern noise can be estimated by averaging a sequence of dark frames for each ISO. And this pattern can also be further investigated for the relationship with ISO settings. Once the fixed pattern noise is subtracted, we can proceed with a centralized Fourier analysis, and a prominent vertical line can be seen in the center of the Fourier image, and which indicates the existence of row noise. And to model this row noise, we calculate the mean values for each row, and which are then fitted to a Gaussian distribution. You can see that the Gaussian distribution will fit it the row noise. And for the remaining read noise, some approaches utilize the Gaussian distribution. to model this noise, while ELD proposed the use of tachy-lambda distribution. And this distribution is utilized as it accounts for the long tail characteristics of read noise. You can see that the Gaussian noise cannot well approximate the read noise. And so the tachy-lambda distribution provide a more accurate model for this noise component. And now we have understood the core concept of noise modeling and calibration, and we will be moving on the final section of my talk, which focuses on the procedure for enhancing low light images based on the noise modeling. In this section, I will walk you through the practical applications of these theories and giving you an example of process through noise modeling, calibration, and also the noisy image synthesis. And first, I will introduce the typical steps for low light enhancement. And low light enhancements with synthetic data are shown. The steps are shown in the figure. First, we need to model and calibrate the camera noise, and then synthesize a large synthetic data set through a noise generation strategy. And finally, we use the large synthetic data set to train our low light enhancement network. And we have explained the calibration process and noise modeling before, and now we need to explain how to generate noise. The noise generation strategy essentially defines how to sample noise parameters given a calibrated noise model. As most of the noise components are related to the ISO or the gain denoted by K, a common way is to build a joint parameter distribution to sample the parameters in a coupled way. As a result, given an ISO or K, we can sample other noise parameters according to the value according to the sampled K, and then use all of the noise components to synthesize realistic training data. In low light enhancement, we need paired low light and normal light images for training. And generally, low light images are amplified before sending to the DNN. You can see that the low light enhancement is typically treated as a denoising task. So the procedure for synthesizing low light image pairs, as seen in the figure, begins with a clean, normal lit image, which is regarded as the ground truth. And we first darken it by a given exposure ratio, like 200 or 300, to simulate the low light condition, and then sample the noise according to the noise model and the parameter sampling strategy. And then we add the noise to the darkened image, and finally we brighten it up to make the input noisy image. So here we have paired training data for low light raw image enhancement. And finally, I will walk through the entire process of the noise analysis to noise model calibration, and finally to the synthesis of realistic low light images in practical. And now I will switch my share screen to a Jupyter notebook. Just wait a second. Okay, can you see my? Can you see the screen?
Yes. Yeah, no problem.
Okay. So to begin with, we calibrate the system gain K for short noise, and we read some flat film frames, and then we crop due to the lens distortion. We crop the center to 200 by 200 region, and then we calculate the noise variance and the estimated true signal, and the variance and signals are then fitted by a linear regression model. And I have explained that the slope for the linear regression model is the parameter K, the overall system K we want for the short noise calibration. And so we plot the regression results here. You can see that we can infer the system gain K by the slope of the fitted line. And then we calibrate the signal independent noise one by one. We first conduct a fixed pattern noise calibration by averaging the dark frames. As you can see, we average many many dark frames at the same ISO setting. And for better visualization, we amplified the image with exposure ratio, so we can see the structure of the fixed pattern noise. And then let's come to the signal, the row noise and the read noise. And we read we first and after performing a centralized Fourier analysis on the dark frame, and we noticed that there is a vertical line in the frequency domain, which indicates the existence of row noise. And then we average each row of the noise, each row of the bias frame, the dark frame, and we fitted the average value by a Gaussian distribution, and the Gaussian distribution is how we calibrated the row noise. And the rest of the noise can be also modeled by a Gaussian noise, but we can see that there is a long-tailed characteristics of this noise, of the red noise. And next, we build the distribution parameter, the joint parameter distribution. That is to say, given system gain K, we can sample other noise parameters. First, we read some dark frames with different ISO settings, and then we estimate the noise for each dark. We estimate the noise parameter for each dark frame, and have a set of noise parameters. Then we build this the set of noise parameters, including both the ISO setting and the other and the parameter for other noise components. And with the set of noise parameters, we can then build the joint parameter distribution. And as a result, we obtain given a signal, given a system gain K, we can sample other noise parameters. For example, the variance for read noise or the variance for the row noise. And finally, we synthesize realistic noise data using the calibrated noise model. We read a normalized image as ground truth, which is shown here. And then based on the clean image, we synthesize noise through the noise model. And here is the synthesize procedure. And the noise is, we first need to sample all the noise parameters for the synthesis. And with these noise parameters, we will then add the noise components one by one. So here you can see that we first can add the Poisson distribution for short noise, and we add rate noise, we add row noise, and we also add the quantization noise. And as a result, we can have a very realistic low light noisy image, which makes as paired data set with the clean image. Okay, now that's the contents that for my talk. Thanks for listening, and let's welcome Professor Zheng to introduce our next topic, the construction of the coaxial system.
Okay, Yunhao, thank you very much. Okay, I will share my screen first. Okay, hello again. I'm Yin Chang from the University of Tokyo. I'm going to share my personal experience on how to build a coaxial imaging system. Okay. In Haiyang's talk, I think we have seen this kind of bi-axis imaging system. Yeah, it can be used to capture paired dark and bright images. So this kind of paired data can be used to train a low lighting enhancement model. Sure, we can slightly change this capture system. For example, we can change the exposure setting of these two cameras. Then we can capture a blurry image and sharp image. And so with such kind of data, we can train a deep learning model. So anyway, so this kind of data captured by this system can be very valuable. This bi-axis imaging system is mainly composed of the object lens and the relay lens, beam splitter, and also two cameras. For simplicity, I will focus on this bi-axis imaging system. However, with the same techniques, we can build a more complex system. For example, the capture system with 3 cameras. So I mean, tri-axis imaging system, or we can even build a more complex one with 4 cameras, this quad-axis imaging system. So this tri-axis or quad-axis system, we can deal with such kind of systems. We can deal with more complex image restoration tasks, like we can have a benchmark with different effects, or we can compare other restoration tasks like frame interpolation. So here, I would first like to show some industry-grade coaxial camera system. So the most famous example, I think, is the 3-chip color camera. So for ordinary digital camera, there is only one image sensor. So to capture RGB trichromatic colors, so basically we have to use this Bayer filter arrays. It has 3 kinds of color filters. However, at every pixel, we have at most 1 color. So basically, we have to use the interpolation algorithm to restore 3-channel images. So this such interpolation algorithm is called demosaicing. Yeah, demosaicing algorithm works fine usually. However, for challenging cases, it will cause false color or zeppering artifacts. So for some application, we need high quality color information. For such applications, people tend to use this kind of prism-based system. And this prism is very special, so it can divide the incoming light into blue, green, and red, 3 branches. And at each branch, we have 1 image sensor. So in total, we have 3 image sensors. In this case, every pixel has 3 colors. It means we have no need to use demosaicing, and all side effects or artifacts coming from demosaicing can be laterally avoided. So actually, there are even more complex co-axis camera system. So for example, I can come up with 2 examples. So this is the RGB NIR near infrared bispectral camera system. And the right hand is the RGB NIR and NIR. I mean, there are 2 near infrared channels, trispectral camera systems. Okay, so even the spectral range is very wide, from 400 nanometers to 1000 nanometers. This kind of coaxis camera system is actually very accurate. For example, the pixel size is around 3.45 micrometer. However, the pixel alignment accuracy is less than 1/10 of the pixel size. Yeah, so it means technically we can build a very accurate coaxis system. Yeah, with this kind of prism-based techniques. However, it's very expensive to make such kind of prisms. So here, I would introduce our low-cost solution with beam splitters. So there are basically 2 kinds of beam splitters, like plate form or cube form. But in theory, yeah, in principle, they're completely the same. It's very, so 1 beam splitter can divide the incoming light into 2 branches. However, it's very flexible because we can use multiple beam splitters. And then, for example, we can use 3 beam splitter, and we can have 4 light branches. So it's very flexible. However, if we use multiple beam splitters, so sure, it will take more space. Sometimes, like the low light enhancement task, we have to introduce additional ND filters, yeah, to reduce the light intensity. So sometimes we will criticize that there's such kind of system with a balanced 50-50 beam splitter. Yeah, in this case, it's also called half mirror. Yeah, it's not very light efficient. Yeah, so in this case, actually we can use unbalanced beam splitter. For example, the ratio can be 90 versus 10 or 70 versus 30. So if we use such kind of unbalanced beam splitter, the light efficiency can be improved. However, there is one thing we have to be careful is installation. So for this kind of unbalanced beam splitter, they are usually delivered, yeah, without this case. So we can purchase such installation case separately and fix the beam splitter with screws. However, the beam splitter is very fragile. Sometimes we want to fix the beam splitter very firmly. However, it's very likely, yeah, to break the beam splitter. And also, if we do not fix the beam splitter very firmly, so it might be slightly move, and then we will have some misalignment issue. So that I will talk about it later. So anyway, the installation is the point we have to take care of. Okay, the next key point is relay lens. So why do we have to use relay lens? Actually, we have solutions to avoid this relay lens. For example, we can use two object lens, object lens 1, object lens 2, behind the beam splitter. Yeah, in this case, yeah, we have no need to use relay lens. However, in practice, we will find that the capture image will suffer from some ghost effect. Yeah, for example, this box, we can see some ghosts of the curtain, yeah, onto this box. So this is caused by the interreflection effect between the two lens. So actually, the object lens is usually lightly coated. Yeah, the coating is to reduce light reflection. However, it's not perfect. A small portion of light will still be reflected, and the beam splitter, yeah, will not work properly with tilted light. So we know that for image areas around the border, yeah, so the reflected light is mostly tilted. So that's why we can see ghost effect around the image border. So personally, I would not recommend this method. Actually, there is another possible way to avoid relay lens. Actually, this method is presented in last year's ESSAV paper. So this paper, they use a beam splitter, yeah, so very similar, and they use the board level camera. Yeah, I mean the camera without a case. I think the reason is try to reduce the distance from the sensor to the camera. Yeah, even with a board level camera, we can see that the lens is still very huge. Yeah, the reason is that with a huge lens, the flange distance can be longer. Yeah, the flange distance, is defined as the distance between the rear part of the lens and the image sensor. The very common C-mount lens has a flange distance of 17.5 millimeter. Yeah, that's very short. So it's very hard to put a prism and in this very short range. So I think that's why the authors use this kind of large lens, because it has a wider flange distance. So I have tried to find some lens with even longer flange distance. So the longest I have found is 85 millimeter. So this lens is used with a very old Pentax film camera. Actually, it's good for this kind of camera system if we only consider about flange distance. However, it's very huge, yeah. And also the 85 millimeter, I think that's almost the maximum we can find. And it's very hard to build like a tri-axis, quad-axis system I have just mentioned, because the flange distance basically will be longer, yeah, than 85 millimeter. So for lightweight capture system, I think that's very important, because basically we want to hold the whole capture system in hand and move freely. Yeah, I would recommend this kind of relay lens-based solution. Actually, we have no need to build this relay lens from scratch. The optical providers like Edmond Optics, they offer many relay lens, and we only need to pick up the right object distance and the image distance, and choose the right magnification ratio. And basically we use the ratio 1, yeah, because in this case the object lens, yeah, we can just use the object lens as usual. So I mean, yeah, we can, as if, yeah, this lens is directly attached to the camera, yeah. And for sure, yeah, we have ordinary issues, like we have to balance between the aperture size and the field of view. Okay, ordinary issues, yeah, as we use a C-mount lens here. One important thing here is that if the object distance, I mean D1, and the image distance D2, if they are not completely the same, yeah, the capture system will still work. For example, if D1 is greater than D2, so the camera cannot see near objects clearly, but however, it can work properly for middle range and long range objects. If D1 is smaller than D2, the camera cannot see far objects clearly, and also the depth of field will be affected. So I mean, it's really important to make sure the object distance and the image distance are completely the same. Yeah, if we use this 1:1 relay lens, okay. Otherwise, it can still work, yeah, but it has some negative effect on the imaging system, but we might not recognize it. So, because this object distance and the image distance, yeah, it's very important. So we need to find nice ways, yeah, to adjust this distance accurately. So there is one component I would recommend. Yeah, is the zoom housing provided by Solabs. Yeah, that's a famous optical component provider. So actually for this component, yeah, we can turn this screw. However, the optical component can translate along this axis, yeah, without rotation. Yeah, it means, yeah, we can adjust this length, the distance, yeah, easily, yeah, without rotate the camera. Yeah, so that's very important for alignment. So I will mention later. So yeah, here I used the two zoom housing. Yeah, one for each branch, and with such zoom housing, yeah, we can accurately adjust the distance and make sure it's D1 and D2, they are completely the same. So this will help a lot in improving the image quality. Okay, here it's about geometric misalignment. Okay, there are several reasons that we still have misalignment, geometric misalignment. As for translation error along the horizontal or vertical direction, the reason might be some accuracy problem between of the two holes of the beam splitter, or due to the position some error of the sensor inside the camera. Yeah, for these two kind of error, so it will cause translation misalignment between two images. Actually, there are also some small rotation errors. So this is mainly caused by the space between the post and the post holder. Yeah, I will show you later in the next slide. Yeah, because there is very small space, yeah, between the rotation between the post and the post holder. So there might be very small rotation angle between these two cameras. So we might have some rotation errors. Sure, we can try very hard and we can adjust them by hand. And I have achieved some accuracy like several pixels. And I think that's the limit we can achieve by hand. However, the question is that, do we really need to adjust them to that kind of accuracy? According to my experience, because this kind of misalignment is almost fixed, and we can use calibration to eliminate this kind of misalignment. So actually, there is a very strong theoretical grounding, yeah, for this kind of correction method. Yeah, I have mentioned this coaxial imaging system because we have only one object length here. It means we have only one optic center. Yeah, so if the distance, object distance and the camera distance, they are accurate, yeah, they're completely the same. It means we have the two cameras have the same optic center. Yeah, in this case, the two images, the transform between the two images, yeah, is a perfect homography. Yeah, it's independent of the scene structure. So it can be planar, it can be any 3D structure. Yeah, so this is grounded on multi-view geometry, and so we can rely on this theory. In practice, yeah, we can use this checker pattern. We can place this checker pattern at different position, yeah, away from the camera lens, yeah, in the working range that we hope we want to capture. And with this checker pattern, we can estimate homography between these two cameras. And then we can use the homography to correct the input image and the ground truth image. For some applications like low light image enhancement, we don't want to touch the low light input because we don't want to break the noise distribution. In this case, actually, we can interpret on the bright images because basically, like for noise synthesis, we assume the bright image is noise free. Yeah, in this sense, yeah, if we interpolate on the bright image, so it's quite safe. So this is a small trick, very helpful in practice. Okay, as for cameras, yeah, there are many cameras, yeah, we can use. However, if we use consumer cameras like a cell phone or DSLR camera, yeah, it's very hard to fix the camera, and also it's very hard to align these cameras. So here I would use the industry camera. Yeah, even for industry cameras, yeah, there are different formats like the board level camera I just mentioned. Yeah, for this we can save the flange distance I have just mentioned. However, we have to consider how to fix them firmly, and also we can use this kind of cased camera. It's easy to fix it. However, we will lose some flange distance. Yeah. Also, the data transfer interface. Yeah, there are many different interfaces like a PG camera. This is basically not very stable for real-time data streaming. So I would recommend USB camera. It's not a perfect solution because of the bandwidth problem I'm going to mention in the next page. However, it's widespread and we can use one cable, and so it's very convenient. And for more stable data streaming, we might use the specialized camera link. In this case, we have to prepare very special interface cards. So here today, I'm just focused on the USB camera. For sure, yeah, we can use global shutter camera or we can use zoning shutter camera. But for low light enhancement for deblur, yeah, basically we use global shutter camera, and it's easier to for synchronization. Yeah, I'm going to introduce later. Okay, because we pre-calibrate the misalignment, so we want to use this homography for all the images we capture. So here, it's important to fix all the optical components very firmly. Our trick is to use this kind of plastic washer between every two optical components. Yeah. If there is an interface, then we just use one, and we can use different thickness here. And then we use the post and the post holder I just mentioned, and then we can fix them very firmly on the breadboard. Previously, I used this kind of post holder just with one screw, and I found this is not very stable because there is only one contact point. Yeah, more recently, I just use this kind of more expensive post holder, and it has a very special locking mechanism, and so you can help fix this post more firmly because there are many contact points here. So in practice, I would recommend to use this more expensive post holder. Okay, the next important thing is synchronization. Yeah, because we have to make sure the two cameras will start at the same time. Yeah, for example, for low light enhancement, yeah, we have to make sure the start and the ending of the two cameras exposure are completely the same. Basically, for industry camera, they offer this kind of master camera and slave camera setting. Yeah, we just need to wiring these two cameras by following their guidelines, and we have to configure the camera software at the master side and configure the software at the slave side. For sure, yeah, this master-slave method will work. But in practice, it's not very convenient because you have to configure many parameters here. And if you ignore one parameter, yeah, by accident, your data, yeah, will completely will not be useful. So in practice, I would recommend this kind of external trigger, yeah, with some signal generator. For example, this one has 2 channels, and we can set the waveform like a rectangular, frequency 20 FPS, the amplitude offset according to the camera we use. We can set the amplitude offset properly. Yeah, we can set for each camera independently, and these signals can be completely aligned. And another point another reason to use this kind of signal generator is that we can also adjust the delay of the 2 exposure easily. Yeah, for some application like deep learn, yeah, we want to make the exposure of the sharp image, yeah, just in the middle time of the blur image. So we have to set up a delay here. Yeah, with this signal generator, we can just adjust the phase, and then we can get a small delay between these 2 signals. Then it's very flexible and very convenient for different applications. Okay, here is about data transfer. Yeah, because we have chosen the USB camera, and the theoretical bandwidth is about 625 megabytes per second. This is just the theoretical value. In practice, the bandwidth allowed is much lower, maybe 1/3, yeah, of the theoretical value. However, the bandwidth required, yeah, can be much larger. Yeah, for example, we can calculate, for example, for about 1,300 by 1,000 for such image at 50 FPS, and the pixel format is mono 16 bits. Yeah, in this case, by simple calculation, we know the bandwidth is more than 160 megabytes, because we have 2 cameras, or sometimes we have 3 or 4 cameras. Yeah, we can easily go over this allowed bandwidth. Yeah, in this case, yeah, if we use desktop PC, we have to use some interface cards. Basically, we have to be careful that for this card, for example, even there are 4 ports, yeah, but they share the same USB channel. Yeah, so basically we have to use this kind of 4 ports, but they have independent channels. Sometimes we use notebooks. Yeah, there are, for example, here we have 3 different ports. We have to double check whether these ports are independent or not. So simple way is that we just plug in 3 cameras, yeah, and we can say at the system part, yeah, it will tell us, yeah, actually 2 cameras, they share the 1 channel, yeah, the other one share 1 independent channel, yeah. So in this case, the bandwidth, yeah, will be halved. So we have to carefully calculate the bandwidth and to make sure our required bandwidth is below, yeah, than the theoretical value. Yeah. So actually, even if we have make sure, yeah, that the bandwidth is okay, in practice, there are still there are some cases that some frames will be skipped, and there are many reasons. Yeah, because maybe due to the CPU, because of the RAM of the PC, or because of the hard disk of the PC. Yeah, in this case, it's very hard to figure out which one is the real reason that caused the problem. But in practice, we have some experience on how to avoid this one. For example, we can we can choose between the streaming mode or buffering mode. Basically, the buffering mode can help avoid this skipped frames. And also we can adjust the package size, okay, with the proper value, and the skip frames might be avoided. For sure, we can reduce the required bandwidth. For example, we can reduce the image resolution. Sometimes we can simply crop the center part of the image, yeah, because we don't need the full image. Also, we can reduce the frame rate maybe from 60 to 30, because 30 is still enough for video recording. Also, there are some other solutions that can be very effective in practice. We need to power, especially if we use a notebook. Yeah, we have to power the PC sufficiently, and also we can power the cameras. Yeah, because the USB camera, the USB port can power the camera, but it's not enough, and we can use independent power supply. Sometimes the PC, the notebook might not good enough. Yeah, we can use a better one. Yeah, this is some very important maybe tricks in practice. Anyway, we have to make sure, yeah, low skipped frames. Yeah, because if some frames are skipped, the whole sequence cannot be used, because we don't know which frame is skipped. Okay, for some application, we need a very high speed capture. Yeah, this is very common for like a frame interpretation task. For some camera, like this FLIR camera with the IMX425, this sensor, in theory, it actually supports more than 600 FPS. But in practice, the maximum FPS is less than 200. The reason is because of the bandwidth of the USB port I just mentioned. And also, yeah, in practice, the actual frame rate may be less than 100 due to many factors I just mentioned. So in this case, I would recommend to use this kind of fast camera with onboard memory. Yeah, this is very important. It means the images, all the images recorded will be saved in the onboard memory. Yeah, after capture, we can transfer the data to the PC. Yeah, actually, for this camera is not very expensive, and we can achieve maybe about 2000. Yeah, if we use 8-bit bit depth. Also, if we need an even higher frame rate, yeah, we can use a specialized fast camera. But this is quite expensive. One last important point is about color composition. If we use different cameras, yeah, different camera basically they have quite different color response, and we need to compensate their color differences. Even if we're using the same cameras, there are still some sources of very minor color differences. For example, the ND filter, yeah, ideally it should be perfectly flat, but in practice, it's not that perfect, and the response can be slightly dependent on the wavelength. It means dependent on the color. And for beam splitter, yeah, for example, 50-50 beam splitter, it's not perfectly 50-50. Yeah, depending on the polarization state of the light, there might be slightly different. Okay, that's also related to the color or wavelengths of the light. In this case, because the difference is very minor, okay, we can use a checkerboard, and we can estimate the color correction matrix. the same, we can pre-calibrate this matrix, and then we can use, we can correct the color. Okay, the last one I'm going to mention is about raw to sRGB transformation. Even we mostly work on raw images, yeah, in especially for the works in this tutorial, but sometimes we need sRGB like for visualization purpose, yeah, because ISP is very complex, yeah, and consumer cameras, they have specialized ISP module, and basically that takes a lot of efforts to tune a proper ISP. As for free software, we can use LibRaw or the Python version RawPy. By comparison, we can find RawPy maybe is not that as good as commercial ISP, especially for automatic white balancing or color saturation. For example, this color looks quite plain, and the commercial one, yeah, it looks quite saturated and looks nice. Yeah, in practice, we can carefully adjust the parameters of this RawPy, and to some extent, yeah, we can get results close to this commercial ISP. Another factor, yeah, we have found is that this kind of automatic white balancing or automatic brightening mechanism in RawPy, so they might cause some flickering effect. So our method is maybe one trick. Yeah, is we just stitch multiple frames into a huge image, and when we use RawPy to process this huge image, then we can avoid this kind of flickering effects. Okay, that's all. Maybe some experience I can share with all of you, and maybe you can borrow some of them to build your own co-axis imaging system. Okay, so finally, we have some time. We can maybe until 12 o'clock. We would like to welcome some questions or comments regarding our tutorial. For Zoom users, Zoom audience, yeah, you can leave your comments in the chat session, or you can just unmute yourself and tell us, yeah, share us with your opinions.
Yes, there's the microphone. Sorry.
I was actually just wondering if the Jupyter notebook for the noise simulation would be available for us to use or experiment with.
Okay. So for in-house, will you be sharing the Jupyter code sessions online after this tutorial?
Haiyang, would you please repeat the question? Maybe Yunhao didn't fully get it, the question.
Yes, sorry. The question is about the calibration for the noise parameters, noise modeling. The Yunhao demonstrated in the Jupyter notebook file. So the audience is asking whether that file will be shared after the tutorial session.
Okay, Yunhao.
Yeah, maybe I will talk with Professor Fu, and perhaps we will release a simplified version, but it consists of the whole process of the image analysis, modeling, and the noisy image synthesis.
Yeah, Yunhao, thank you.
Thank you for the question.
Any other questions?
thanks for talk. I have a question about the coaxial optics. So, are you aware of any consumer electronics such as phone, tablets, laptops that use the coaxial optics or similar design? Yeah.
Thank you very much for the question. Haiyang, would you please repeat, because it seems the audience is far away from their mic.
I see. Maybe can you just try this one? This one here. Sorry.
Yeah, thanks for the talk. So my question is that, are you aware of any consumer electronics such as phone, tablets, or laptops that have this like a coaxial optics or such? Yeah, that's basically my question.
Okay, do you mean the 4-axis system?
Yeah, any consumer electronics that already like use such design. I know you show
okay.
some like cameras, which like case cameras that has have similar setup, but for the smaller version of the for the consumer electronics, which has higher requirement in the form factor or the size that.
Okay, thank you very much. I was go back to that page. Yeah, do you mean some consumer product similar to this kind of camera?
Yeah, exactly.
Yeah, actually, I have to say, yeah, this kind of camera, like this bispectral camera or trispectral camera, and also this kind of three color camera, a 3-chip color camera, they are mostly used for a very specialized area. For consumer grade product, I think because it's quite expensive, yeah, much more expensive than this kind of single chip solution. To my knowledge, yeah, I don't know any like consumer level, and what I have found it mostly is for this kind of very special application scenarios.
Yeah, one more question related to this. So do you see any blockers except the price? Any blockers that to make it to be a very small form factor and make it to the consumer electronics like phones?
If you look at, if you go to the web page of this product, you will see the form factor is actually not that huge. Yeah, especially for the bispectral one, the form factor is kind of compact. Yeah, is not sure it's not as compact as this kind of single chip camera. But sure, yeah, if you have the 3-channel version, the size will be larger. But I think the form factor maybe is not the major problem, I think.
Okay, thank you.
Yeah, thank you very much. Okay, I got a question regarding whether we will share the slides. Okay, so we will try to including the source code, yeah, by Yunhao. Yeah, we will try to find a good way, yeah, to share the information we have shared today. Yeah, thank you very much. Okay, I think it's 12 o'clock. If we don't have further question, so I would like to end this tutorial session. I would like to thank all the audience online and on-site for coming to our tutorial. And also I would like to thank our guest speakers, organizers, yeah, for this tutorial. Thank you very much. Okay, so I think we can leave for have a nice day.
吃饭去。